Hello, I am Gideon Billings with the Deep Robot Optical Perception Lab at the University of Michigan. This video presents our work to develop a simple-to-use software tool for aiding the process of underwater camera and lighting system design. This tool aims to expose the most significant design parameter considerations for an underwater optical system and provides an intuitive interface for quickly analyzing the effects of different hardware and parameter specifications. Optical camera systems have grown in popularity for underwater imaging applications ranging from benthic surveys to ROV operations, due to their low cost and the richness of their captured information. However, designing an underwater imaging system is a complex task with a large space of hardware selection. Critical hardware considerations include the choice of sensor, lens, and lighting, with specifications of the components having a great impact on the overall imaging performance. The process of designing and tuning such a system can be labor-intensive, involving iterative adjustments of imaging parameters, followed by careful field tests and image quality verification. In this work, we present a simplified underwater image formation model, which operates as a backend to our software tool to inform the initial design choices and different parametric effects on the imaging performance. Let's say we have an underwater vehicle outfitted with a downward-facing camera and strobe for imaging the seabed. Assuming the only source of light is the vehicle-equipped lighting, the image formation process starts with a burst of light when the strobe is activated. As the light propagates through the water column, some amount is attenuated due to absorption and scattering events. The attenuation is described by an exponential function where r is the initial irradiance from the strobe, b of lambda is the wavelength-dependent attenuation coefficient, and d is the distance the light propagates. When the light reaches the seabed, it is reflected back towards the camera, where the reflection is modeled using a bidirectional reflectance distribution function that relates the reflected radiance from the surface, L, with the incoming irradiance, E. Our model assumes diffuse reflection, where theta sub I is the light incidence angle, and m of lambda is the material and wavelength-dependent reflection coefficient. As the reflected light propagates back through the water column, it experiences further attenuation due to the absorption and scattering. Once the light reaches the camera viewport, it is refracted through the water glass, then air interface. For a flat viewport, refraction has the effect of increasing the effective camera focal length by the index of refraction of water. For a dome port with the camera centered, the effects of refraction are negated by the curvature of the dome, and the effective focal length remains the same as in air. As the light travels through the camera lens, there are lensing effects described by the fundamental radiometric relation, which describes the amount of light incident on the lens that actually reaches a pixel at the sensor surface. In this equation, L is the seen radiance, N is the lens aperture number, alpha is the angle between the principal ray and the ray through the pixel, and the cosine term models natural vignetting. Some light is also lost as it travels through the lens according to the lens transmittance efficiency. Light that reaches the camera sensor is converted into an electrical signal. We assume a linear response function which is typical for machine vision cameras. The dependency of the sensor response on wavelength is described by the sensor quantum efficiency curve, and the total number of absorbed photons, mu sub e, is computed by dividing the spectrum energy weighted with the quantum efficiency curve by the energy of a photon. The digital sensor response is then calculated as the sum of the sensor mean dark signal and the number of absorbed photons multiplied by the system gain k. We experimentally validated this camera response formation model with a lab water tank setup illustrated in this figure. A camera and strobe were mounted outside of a clear acrylic freshwater tank, and a diffuse white target board was placed on the opposite inside tank wall. We used a spectrometer to measure the light signal at the target board and the signal received at the camera lens. The measured light signal at the target board and the camera lens closely matched the spectrums predicted by the model. We measured the sensor response for two different sensors while keeping the seen lighting constant and increasing the sensor exposure time, and it was verified that the model predicted sensor response curve matches the measured values. We also conducted a second set of experiments using the same camera sensor, but changing the lens focal length and aperture values. Again, the measured values match the model predictions, confirming that the model is a good approximation for real camera systems. I will now walk through an overview of our underwater camera system design tool with a demonstration of how it can inform the design process. The tool is implemented in Python with a Qt user interface. A well-designed camera system should capture exposed images with adequate signal-to-noise ratio, no motion blur, and a depth of field covering the desired range of benthic topology. This tool acts as a front end for the image formation model to estimate the image signal based on the operational and environmental parameters. In the top section, we can configure our lighting parameters. Currently, the tool only supports the generic LED spotlight, though there are other options in the drop-down that are planned to be supported in the future. The spotlight parameters include the luminous flux and the beam half angle. Pressing the info button shows a plot of the light spectrum. I will set the half beam angle to 45 degrees for now. Next, we can choose the water attenuation profile based on the expected operational environment. The profiles follow the Gerlov classification scheme from clear to turbid for oceanic and coastal waters. Different attenuation profiles can be compared by selecting them and pressing the info button to show a plot of the spectrum. For now, we will keep the water type as Gerlov 1, which approximates clear oceanic water. The camera lens can be configured as a generic lens with the desired focal length and a constant transmittance across the full spectrum, which is generally a reasonable approximation. In the case that the transmittance varies significantly across the spectrum, for example, when a color filter is used, the tool does support loading a custom lens model with a specified transmittance spectrum. Pressing the info button displays a plot of the lens transmittance spectrum, which is just a constant for the case of the generic lens. The effective focal length of the lens underwater is also shown, which for a flat viewport is adjusted by the index of refraction of water. There are several common machine vision camera sensors included with the tool, and new sensor models can be added easily. We will select the IMX250 monochrome sensor for now. The tool displays the sensor specifications, and pressing the info button shows a plot of the quantum efficiency. The next section is a set of operational and scene parameters. The altitude is the target height from bottom that the vehicle will be surveying. We set this to 2 meters. The overlap specifies the desired overlap between consecutive images, which is important when stitching images or generating scene reconstructions. This parameter only affects the minimum frame rate, so we will leave it at 25%. The speed setting is the expected speed at which the vehicle will fly while conducting the survey. The max motion blur affects maximum exposure time. In general, the max motion blur should be 1 pixel for image processing methods to work robustly, unless the pixels will be binned or subsampled. The aperture controls the depth of field, but also affects the image exposure. We will set the aperture to 4 to increase our near depth of field limit. The camera orientation is relative to the direction of vehicle motion and affects the minimum frame rate calculation to obtain the desired image overlap. The housing viewport type can be set to flat or domed. We will keep it as flat for now. The index of refraction of the viewport material can be changed, though this is only important for a dome viewport. There is a selection of different bottom types that can be selected based on the expected operational environments, ranging from sandy bottom, which is most reflective, to organic, which is least reflective. These selections represent rough average reflectivity values. We will select benthic average for now. The bottom section shows the output of the model based on the selected parameters. The only configurable parameter in the output is the exposure time, which can be set up to the maximum exposure value. The output includes the focal depth of field limits, the max exposure time, the image field of view, the image signal-to-noise ratio, the average image intensity, and the minimum recorded frame rate. The two main output parameters which drive the system constraints are the average image intensity and the signal-to-noise amplitude ratio. The desired signal-to-noise ratio should first be determined, and then the design parameters should be adjusted to achieve this value. An analog gain can then be added to achieve the desired average image intensity for proper exposure. In this example, I will aim for a signal-to-noise ratio of at least 20 and an average image intensity of around 40%. Given the current operational parameters, the first thing I can do is adjust the light power to achieve the desired signal-to-noise ratio, which in this case is 30,000 lumens. To achieve the target average image intensity, I need to add a gain of 7.5. I will now change the viewport type to a dome. The model assumes the camera is centered in the dome, which makes the effective focal length underwater the same as in air. Some additional parameters for the dome viewport can be set as well, including the external dome radius and the dome thickness. Because the effective focal length is lower with a dome than a flat viewport, the max exposure time limit to achieve subpixel blur is higher, allowing an increase of the image exposure time for a better signal-to-noise ratio. I can also reduce the lighting power if desired while still achieving the desired minimum signal-to-noise ratio. The optics of a dome viewport compress the focal distance to a virtual image at some distance less than 3 radii in front of the dome. This virtual image distance is also displayed in the output, measured relative to the external vertex of the dome, and the camera should be focused to this distance in air to achieve the desired focal plane underwater. I will now try a different camera sensor, the IMX249, which has larger pixels than the IMX250. The larger pixel size enables a higher exposure time, and I can also greatly reduce the lighting power while achieving the desired signal-to-noise ratio. In this case, I can reduce the light power to around 3000 lumens. The tool supports color sensors, but approximates the pixel response using a Bayer average, as though the image were converted to grayscale. Due to the Bayer pixels, color sensors have poorer overall quantum efficiency compared to their monochrome counterparts. I can now change the water types and observe the effects on signal-to-noise ratio and image exposure. It is observed that more turbid waters greatly decrease the imaging performance. I can also change the bottom type and observe the effects on the output parameters. The lighting requirements between imaging sandy bottoms versus imaging organic bottoms, such as bacterial mats, are significantly different. In general, the bottom type and water attenuation profile should be selected for the most conservative operational expectations. This tool is open source and can be downloaded from this GitHub repository. We plan to actively maintain this tool and add additional features in the future. Thank you for watching.